Okay.
So large because of the secret.
Yeah, it's nuts. There's a horse with red eyes at the entrance.
What?
Yeah, there's a giant horse with red eyes at the entrance. There's tons of murals with ridiculous things on them. It's nuts. There's a
Okay.
mural of the soldier around.
Let's go ahead and start. I can't take it anymore. Okay, so two other things that I need to test your ability to accomplish on this test. One is just simple vector addition. A descent vehicle landing on Mars, and we did this one in class, has a vertical velocity towards the surface of Mars, 5.5 meters per second, a horizontal velocity of 3.5 meters per second. At what speed does the vehicle move along its descent path, and at what angle with the vertical is it? And your goal is to show me that you know how to do vector addition here. You will say that you have one vector in the vertical direction towards the surface, and you're going to call that V1 or V whatever you want. You can call it VA or VX or something, or VY if you wanted to. But you need to label it and say that it's 5.5 meters per second. And then you need to have a second vector in the horizontal. V2 equals 3.5 meters per second. Don't know how that happened. Okay, and so to add these vectors together, you know that you just simply start at the beginning of the first vector and end at the end of the second vector, and that's your result. That tells you what the overall velocity is. This will be the velocity of the vehicle along its descent path. Its descent path is this angle thing here. And you know how to find the velocity. And again, the purpose of the diagram is so that you can create your formula. Now that I know I have V1 and V2, I can say that V equals V1 squared plus V2 squared. So I need to see that formula. Then I need to see substitution into the formula. 5.5 meters per second squared plus 3.5 meters per second squared. And so my actual velocity, and I forgot what it was going to be. Kirsten's going to figure it out for me here real quick.
Three. Oh wait, I forgot.
It's not 3.
My bad. Six point five.
6.5 meters per second. Okay, and then I need to know what this angle is. And when I'm finding an angle, your question always is, what two sides do I have? And you look at this and you say, I have the opposite side. I have the adjacent side. Therefore, I have to use what function to find the angle? I have to use tangent because TOA, right? So TOA. And I know that tangent of theta equals opposite over adjacent. Therefore, I know angle equals inverse tangent of opposite over adjacent. And you don't have to take the step where you say tangent inverse over V2 over V1 if you don't want to. You can go directly to the numbers there if you want to, because you've got a formula, and that's all I need. But if you want, you can also say tangent inverse of V2 over V1, and then tangent inverse of 3.5 over 5.5. And we don't need the units here because it's just a ratio. And Kirsten's going to tell us that is how many degrees?
32.47.
So 32.5 degrees. So the angle from the vertical is 32.5 degrees. Okay? It should just take you a couple of minutes if you are familiar with this. And that would be, and so I may change the scenario a little bit, but it'll still be something where something is coming down and vertically. Okay? Any questions about that problem? Okay? Basic vector addition. You have to be able to do that. Can I move? You weren't actually writing on the table where you gave?
No.
Okay, because if you are, I'm going to ask you to clean my tables. Because people are writing too much on my tables and it's pissing me off.
What constitutes too much?
Huh?
What constitutes too much?
At all?
Oh.
Okay? If you're writing on my tables at all, that's vandalism. It's against the law. And it takes me a long time to clean them, and I don't want to do that. Anyway, the jet that you're flying on to Disneyland takes off at a velocity of 134 meters per second at an angle of 27.4 degrees. What are the horizontal and vertical components of the velocity? You do understand this skill also from angled launch, but I want a separate problem here showing that you understand this basic principle. I've got a plane taking off at an angle of 27.4 degrees, and the velocity is 134 meters per second. And we use the idea of vector addition, and we go backwards. I've got the final result, right? I've got the final result here. I want to know what the two vectors are that I add together to get this final result. My final result is the velocity of 134 meters per second. I want to know what the vectors are that I add together to get that. And I know that this is the adjacent side and this is the hypotenuse. So when I want to find this side, the velocity in the x direction, I know I'm going to have to use the cosine. What side do I have? Hypotenuse. What side do I want? Adjacent. Therefore, I have to use the cosine. And if I forget this formula, most of you probably remember by now that it's just v times the cosine of theta. But if I forget it, you're going to write out the definition of cosine. Cosine of theta equals adjacent over hypotenuse. And in this case, that's Vx over V. And you say, I want Vx, so I have to multiply V times the cosine of theta. And voila, you have that formula. And then same thing for the vertical velocity, or the ascent. I have Vy equals, and if you don't remember that it's V times the sine of theta, then you can say, oh, I have the opposite and the adjacent, and I know that that's going to be the sine. I can come over here and say sine of theta equals opposite over hypotenuse, which is the same thing as Vy over V, and I can calculate that then as well. And so 134 meters per second times the cosine of 27.4 degrees equals what, Kirsten?
For cosine?
For Vx, yeah.
118.
118?
Yeah. Because it was 118.96.
Okay.
Oh, wait, 119. Sorry, my bad.
So 119.
Yeah.
Okay. 119 meters per second. And we can see that, that kind of makes sense. This is about 119 134ths, right? The ratio of this to this, it would make sense that it's about that much. And then if I want to talk about the opposite side, V times the sine of theta is going to be 134 meters per second times the sine of 27.4 degrees. And what did you get for that, Kirsten?
61.7.
61.7 meters per second. How do I know that that's about right? What do I know that the sine of 30 degrees is? 1/2. So I know that my answer should be almost 1/2 of what the hypotenuse is, and it is, right? It's almost 1/2 of that, so you know that you got the right answer. Okay, so that's all I want for that problem. Tell me what the ascent speed and tell me what the ground speed is. And I'll probably change that to a little bit of a different scenario as well, but it'll still be one where you've got something that's flying at that angle, and I want the ground speed and the ascent velocity. Any questions about that? Okay, now I want you to look at your study guides and ask any last minute questions right now. Something you don't understand. I'm not sure how you did this, Marshall. I know I've got the explanation right there, but I don't want there to be any excuses for anybody not doing well on this test.
I think we just going over number 4, but it's basically the same thing.
Which one?
Number 4, but it's basically the same thing what we just did.
Follow sort of lot, yeah. It's exactly what we just did. Okay, so is there something that you're a little confused about by that still?
No, not really.
Okay.
And I have some difficulty to remember what the formulas are that we need to use.
Okay, so, I mean, you'll have the formulas on the test. I'll give you the formulas on the test. But you do have to be the one that knows which formulas to use. Is there something specific that I can help you try to remember, or? Okay, so one of the things that you have to sort of make a distinction of here, and let me just kind of review that idea. First of all, for horizontal and angled launch, for motion in 2 dimensions, we have a formula that tells us about motion in the x direction and, oops, not y. We remember that motion in the x direction is constant. Okay, it does not change. Its velocity is the same throughout the entire flight. Okay, and that's why I have to use the constant velocity formula here. I want to know how far it goes in the x direction. In all of our problems, x0 is always going to be 0. That's always going to drop out. But I know that how far I go in the x direction is going to be the velocity in the x direction times time, and that's the only thing that I can use to find out information about something in the x direction. Okay, it's the only way I can find out how far I went or what the velocity in the x direction was. I can use any of my formulas to find out what the time is, but I should use formulas in certain circumstances to find out what the time is. Most of the time when you have horizontal launch, you're going to want to either know how far it goes or what the velocity is. And in order to do that, you're going to have to find time, because I won't give you the amount of time it takes unless I'm really generous. And you already know what those problems are going to be. But in order to do that, in order to find time, in a horizontal launch, you're going to have to use y equals y0 plus vy0 times time plus 1/2 at squared, okay? You don't have any choice. So that's one of my y formulas, y equals y0 plus vy0 times time plus 1/2 at squared. And the nice thing about horizontal launch is this term drops out. So all I end up having to do, and some of you will actually go into this test having memorized this, the time is going to equal the square root of 2y or negative 2y0 over the acceleration. Some of you will have memorized this. I'm not going to put this on the test, but in order to find time, you'll have to find that that's the case. So in order to get that, I remember that this is going to be 0. So I move this to the other side and it becomes negative, and then I multiply that times 2 because I want to get rid of this denominator. And then I'm going to divide by a, and I know that a is going to be negative as well, so I don't really have to put my negative signs in there. And then in order to get t, I'm going to have to take the square root of that. Okay? I really, 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 really want all of you to start to get a good feel for how to isolate variables. Okay? That's the way that all of this becomes intuitive to you, and it starts to make a lot more sense. If you know how to put one of these variables on the other side by itself, it becomes a lot easier to see how things are going to work. So horizontal launch, you need to find time using this formula, and it boils down to t equals the square root of negative 2y0 over a. On the other hand, if you have a angled launch and you need to find time, if you have an angled launch and you need to find time, you're probably not going to be able to use this formula because you're not going to know how far the person went yet. So you won't be able to use this. And you certainly can't use this formula because Vy0 is not 0 in this case on an angled launch, right? Vy0 has an initial value, which you'll have to figure out, right? Vy0 has that value that you'll have to figure out, which will be V times the sine of theta, right? And then that leaves you with the third formula that we have, Vy equals Vy0 plus AT. But the nice thing about this is that the initial y velocity is the same thing as the final y velocity, okay? And since I know that Vy equals the opposite of the initial velocity, I can substitute that in. I can say negative Vy0 equals Vy0 plus AT, and then I can solve for t again, and that's going to turn out to be t equals negative 2y0 over a. And notice the only difference here between finding time that way and finding time this way is that finding time during an angled launch, it's the same formula, except I don't have to take the square root of it. It's the same formula, but I don't have to take the square root of it. Okay? So, I mean, we've been through that, and a lot of that explanation is in the explanations in the handout. So hopefully, having heard that now for the 4th or 5th time, that all of this starts to sink in. Other questions? This stuff is pretty difficult. Even college freshmen have a hard time with this. But I still have to teach it to you. So some of you get this, some of you not so much, and that's okay. But this practice that we're accomplishing will make it better. Other questions about this test? Other things that you still find confusing or will be difficult for you?
I can't think of anything specific, but I am wondering what a laryngologist is.
You're wondering what?
Laryngologist, I don't know specifically one of the larynx.
Oh, this? Otolaryngologist. Oto means ear, and larynx means the tube that goes down to your, right, that has your voice box. So this is an ear, nose, and throat doctor. The actual term is otorhinolaryngologist. So if you know that oto refers to ear, and you know that larynx refers to throat, what do you think rhino probably refers to? Your nose. You may have heard of a rhinitis. Rhinitis is inflammation of the nose. In other words, you've got a runny nose. If you've got a rhinitis, you've got a runny nose. And if you get a nose job, that's called a rhinoplasty. Not rhino like with the horn, but
But then, isn't the horn on the nose?
yes. I guess that does kind of make sense, doesn't it? Is rhinoceros spelled with an RH?
Yeah.
Okay.
It's literally
Okay.
rhino, the shortened is literally
Okay.
like that.
So, nose dinosaur. I never thought about that before. Otorhinolaryngologist, your nose and throat. Anything interesting otherwise? If there's not, I'm just going to give you the rest of the time to continue to review on your own, or if you have other things that you need to do those things. Okay? So, Kate and Gabe, how can I help you guys get ready for this? What are you going to say? If you have any questions, give me time. Make sure you look over it really thoroughly and just catching up on early Tuesday.
We're looking at
Yeah. So catching up on
which I was.
I've been helping you.
I'm gonna.
Seriously? Okay, so if you look at this over here.
Oh, the screen is sitting there.
Okay. You guys are awesome.
And get your pin right, Tam. Struggle bus.
I didn't know that.
Struggle bus.